In this video, we will talk about trigonometric ratios or trigonometric functions, then directed angle, radian measure, relation between degree and radian measure, trigonometric ratios, their definitions, signs of trigonometric functions in different quadrants in Cartesian coordinate system, and trigonometric identities. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. Consider ray OA. Suppose we rotate ray OA in anticlockwise direction about point O to take a new position ray OB. Then the amount of rotation of ray OA in anticlockwise direction is known as directed angle AOB. And since this rotation is anticlockwise, this angle is treated as a positive angle. Consider again ray OA. Suppose this time if we rotate ray OA in clockwise direction about point O to take a new position OB, then the amount of rotation of ray OA in clockwise direction is called directed angle AOB. But this time, since the rotation of ray OA is in clockwise direction, this angle is treated as minus. Coterminal angle. Angles which have same positions of the initial arm OA and final arm OB, but they differ by integral multiples of 360 degrees, then they are called coterminal angles. Suppose the directed angle AOB is theta degrees. If we rotate ray OA in anticlockwise direction in the amount of 360 plus theta degrees, 360 plus theta degrees, so that it will again take the final position of ray OB. Then this angle theta and the angle 360 plus theta degrees are called coterminal angles. Suppose the directed angle POQ is 30 degrees. If the initial arm OP is rotated about O by making one complete rotation and then again by making one more rotation, finally reaches the terminal arm position OQ, then this directed angle will be of the measure 30 degrees plus, since it has made two complete rotations, so 2 multiplied by 360 degrees, that will be 30 plus 720, or which will be 750 degrees. So this 30 degrees and this 750 degrees will be called coterminal angles because the positions of their initial arm and the terminal arm are the same, but their measures are different. In system of angle measurement, we will study two systems. The first being sexagesimal system. In sexagesimal system, a right angle is divided into 90 equal parts. Each part is called 1 degree. This 1 degree can be divided into 60 equal parts. Each part is called 1 minute. Now this 1 minute is divided into 60 equal parts and each part is called 1 second. Here, since the subdivisions are of 60 parts, therefore it is called sexagesimal system or simply degree system of angle measurement. The second system of angle measurement is circular system or radian measure. Radian is a special measurement of an angle. It is defined as 1 radian is the angle made at the center of a circle by an arc whose length is equal to the radius of the circle. So this is the length of the arc, which should be equal to the radius r of the circle. So in this case, this angle is known as 1 radian and it is written as 1 to the power c. So we have here length of arc AB, which is L. It should be equal to the radius of the circle. Then the directed angle AOB is equal to 1 radian and it is written as 1 to the power c, where c stands for circular system. Radian measure of angle measurement is very convenient in calculus. If the angle is in degree measure, then it is first converted into radian measure and then used in calculus. Let us understand relation between degree and radian measure. Consider a circle with center O and radius r. We have seen that when the length of the arc equals radius of the circle, then the directed angle made at the center of the circle is 1 radian. Now we can argue like that when the length of the arc L equals radius r, then angle made at the center of the circle is 1 radian. And when length of the arc equals circumference of the circle, which is 2 pi r, the angle made at the center of the circle is 360 degrees. Taking ratios, we write r upon 2 pi r equals 1 upon 360 degrees. This r gets cancelled. By cross multiplication, we write 2 pi into 1 radian is 2 pi radian equals 1 into 360, that is 360 degrees. So that gives us pi radians is equal to 360 degrees by 2, which will be 180 degrees. So here we get a very important relationship between degree and radian measure, which is pi radians equals 180 degrees. Next we will see how to use this relation. Let us understand how to convert degree measure to radian measure and vice versa. We have seen that pi radians is equal to 180 degrees. So therefore 1 radian will be equal to 180 by pi degrees. Conversely, 1 degree will be equal to pi by 180 radians. So in order to convert radian measure into degree measure, we have to multiply the radian measure by 180 by pi to get the degree measure. And when we want to convert degree measure into radian measure, then we have to multiply the degree measure by pi upon 180. For example, if I want to convert 30 degrees to radian measure, then it will be 30 multiplied by pi by 180. So that will be, this 0 cancels, 3 ones are 3 6 are, that will be pi by 6 radians. Next, if I want to convert 60 degrees into radian measure, then I shall have to multiply 60 pi by 180. This 0 gets cancelled. 6 ones are, 6 threes are, so that will be pi by 3 radians. So in this way, we can convert degree measure into radian measure. On the contrary, suppose we want to convert pi by 2 radians into degree measure, then we have to multiply pi by 2 by 180 by pi. This pi gets cancelled. 2 ones are, 2 nines are, 2 zeros are. So that gives us 90 degrees. Suppose we want to convert pi by 4 radians into degree measure, then we have to multiply pi by 4 by 180 by pi. This pi gets cancelled. 4 ones are, 4 fours are 16 and 4 fives are 20. So that gives us 45 degrees. So pi by 2 radians is 90 degrees and pi by 4 radians is 45 degrees. So this is how we can convert a radian measure into degree measure. Now we will understand trigonometric functions which are nothing but trigonometric ratios. For that, first we will consider a unit circle, which means a circle with radius 1 unit. We will take a point P, X, Y on this unit circle. We will connect center O and this point P, X, Y. We will draw a perpendicular from P onto this horizontal radius OA. Let the foot of the perpendicular be M. Since this is a unit circle, its radius OP will be 1 unit. Now, since the coordinates of point P are x, y, we have OM equals x and PM equals y. Let the directed angle AOP be theta degrees. Now we will write the trigonometric ratios. The first is sine theta, which is defined as PM upon OP, which will be y upon 1 or y, OM upon OP, which will be x upon 1 or simply x. Tan theta will be PM upon OM, that will be y upon x. Cosec theta is reciprocal of sin theta, so it will be 1 upon y. Sec theta is reciprocal of cos theta, so it will be 1 upon x. And finally, cot theta, which is reciprocal of tan theta, so it will be x upon y. Now in the right triangle OMP, by applying Pythagoras theorem, we write OM square plus PM square equals OP square, which is x square plus y square equals 1 square, that is 1. But x is cos square theta, y is sin square theta equals 1. So this is the first identity that we get, sin square theta plus cos square theta equals 1. We will block this identity for ready reference. Let us talk about the signs of trigonometric functions in different quadrants. For that, we have drawn a unit circle whose radius is equal to 1 unit. So this is x dash and this is y dash. So this will be the first quadrant, this will be the second quadrant, this will be the third quadrant, and this will be the fourth quadrant. Now we will decide the signs of different trigonometric functions when the point on the unit circle is in different quadrants. When the point P is on the positive x-axis, then its coordinates will be 1, 0. When the point P is in the first quadrant, its coordinates will be xy. Suppose if we join origin with P, then the directed angle will be theta, so that the coordinates of P will become cos theta, comma sin theta. Since both cos theta and sin theta are positive, all the trigonometric ratios in the first quadrant will be positive. Now we will take a point on the unit circle which is also on the y-axis, so its coordinates will be 0, comma 1. Suppose point P on the unit circle lies in the second quadrant, then its coordinates will be minus x comma y. If we join point P and the origin, the directed angle will be theta degrees. So the coordinates of P will be minus cos theta sin theta. Since sin theta is positive, only sine and cosec trigonometric ratios will be positive in the second quadrant and the remaining ratios will be negative. If the point P is on the negative x-axis and on the unit circle, its coordinates will be minus 1, comma 0. If the point P is on the unit circle, its coordinates will be minus x comma minus y. If we join point P and the origin, the directed angle XOP will be theta degrees. Say, then the coordinates of P will be minus cos theta comma minus sin theta. Now since both cos and sin are negative, therefore tan theta, which is sin theta by cos theta, and cot theta, which is cos theta by sin theta, will be positive. So therefore tan and cot ratios will be positive in the third quadrant and the remaining ratios will be negative. If the point P is on the negative y-axis and on the unit circle, then its coordinates will be 0 comma minus 1. And if the point P is on the unit circle and its coordinates will be P x comma minus y. If we join the origin with point P, then the directed angle XOP will be say theta degrees. Then the coordinates of P will be cos theta comma minus sin theta. Now since cos theta is positive, cos theta and sec theta, these two ratios will be positive in the fourth quadrant and the remaining ratios will be negative. We can remember the signs of the trigonometric functions like this: x-axis, y-axis, origin, first quadrant, second quadrant, third quadrant, and fourth quadrant. In the first quadrant, all trigonometric ratios are positive. In the second quadrant, sine and cosec ratios are positive. So we write S, which represents sine and cosec, and the remaining ratios to be negative. In the third quadrant, tan and cot ratios are positive. So we represent these two ratios by T and the remaining ratios will be negative. And in the fourth quadrant, cos and sec ratios are positive, which we represent by C, and the remaining ratios will be negative. So this is how we can remember the signs of trigonometric functions in different quadrants. We will see how to remember trigonometric values of some standard angles. There are standard charts available from which you can find trigonometric values of these standard angles. But I prefer to remember these values from the basics. Let us see how we can do that. We will draw a 30 degrees, 60 degrees, 90 degrees right triangle. Let length of hypotenuse be 2. The side opposite to 30 degrees is 1 and the side opposite to 60 degrees is root 3. These values are obeyed by the Pythagoras theorem because 1 square is 1, root 3 square is 3, which is equal to the hypotenuse square, which is 2 square, and that will be 4. So therefore 1 plus 3 equals 4. Hence the values which we have assigned here follow the Pythagoras theorem. Therefore these values are correct values. If we know basic definitions of the trigonometric ratios, then from this triangle we can remember 6 trigonometric values for angle 30 degrees and 6 trigonometric values for this angle 60 degrees. Let us see how. Now sine 30 by definition is opposite side upon hypotenuse, so it will be 1 by 2. Cos 30 by definition is adjacent side, which is root 3 upon hypotenuse, which is 2. Tan 30 is by definition opposite side, which is 1 by adjacent side, which is root 3. Now cosec 30 is reciprocal of sine 30, so it will be 2 upon 1, that is 2. Sec 30 is reciprocal of cos 30, which will be 2 upon root 3. Cot 30 is reciprocal of tan 30, so it will be root 3. So here we got 6 trigonometric values of angle 30 degrees. Similarly, now we will write 6 trigonometric values of angle 60 degrees. So here we write sine 60 by definition is opposite side, which is root 3, by hypotenuse, which is 2. So sine 60 is root 3 by 2. Cos 60 by definition is adjacent side, which is 1, upon hypotenuse, which is 2. So cos 60 is 1 half. Tan 60 by definition is opposite side, which is root 3, by adjacent side, which is 1. So tan 60 is root 3. Now cosec 60 is reciprocal of sin 60, so it will be 2 by root 3. Sec 60 is reciprocal of cos 60, so it will be 2 upon 1, that is 2. And cot 60 is reciprocal of tan 60, so it will be 1 upon root 3. So this triangle alone gives us 6 trigonometric values of angle 30 and 6 trigonometric values of angle 60. That means in all we get 12 trigonometric values. Consider a 45 degrees, 90 degrees right triangle. Let the hypotenuse be root 2 and the sides opposite to 45-degree angles be 1 each. If we check the validity of these values, then according to Pythagoras theorem, we find them to be correct. 1 square is 1. Again, this 1 square is 1, and the hypotenuse root 2 square is 2, and 1 plus 1 is 2. Since these values obey the Pythagoras theorem, the values which we have assigned are correct. Now with the help of these values, we can get 6 trigonometric values for angle 45 degrees. We write sine 45, which is by definition opposite side, which is 1, upon hypotenuse, so it will be 1 by root 2. Cos 45 by definition is again adjacent side, which is 1, by hypotenuse, which is root 2. So cos 45 is 1 by root 2. Tan 45 by definition is opposite side, which is 1, by adjacent side, which is 1. So that will be 1. Cosec 45 is reciprocal of sine 45. So it will be root 2 by 1, that will be root 2. Sec 45 is reciprocal of cos 45, so it will be root 2 by 1, that will be root 2. Cot 45 is reciprocal of tan 45, which will be 1. So from this triangle alone we get 6 trigonometric values of angle 45 degrees. Consider a right triangle A, B, C, which is right at B. So that we write sin C equals by definition opposite side AB upon hypotenuse AC. Similarly, cos C will be by definition adjacent side BC upon hypotenuse AC. Now we will consider a situation in which this point A is slowly approaching point B and finally falls on point B, so that this angle C goes on reducing, and finally when point A lies on point B, angle C becomes 0. So we write sine 0 equals. At the same time here also angle C becomes 0. So we write cos 0 equals. Now let us see what happens to length AB. Since point A is coinciding with point B, points A and B will be one and the same, so length AB will be 0. So in place of AB we write 0. What happens to hypotenuse AC? When point A coincides with point B, hypotenuse AC becomes side BC. So in place of AC we write BC. That gives us sine 0 equals 0. Now let us see, when point A coincides with point B, what happens to BC? BC will remain BC. And what happens to hypotenuse AC? AC will become BC. So we write BC upon VC, which will be 1. So therefore cos 0 will be 1. So we get these two trigonometric values, sin 0 equals 0 and cos 0 equals 1. The right triangle ABC right at point B. In this right triangle we have sin C equals opposite side AB upon hypotenuse AC, and cos C will be adjacent side BC upon hypotenuse AC. Now consider a situation in which point C is slowly approaching point B and finally coincides with point B, and during that period hypotenuse AC will take positions like this, and we observe that angle B is slowly increasing, and finally when point C and B coincide, angle C will become 90. So we get sin 90 equals. Now let us see what happens to AB. When points C and B coincide, AB will be AB itself and AC becomes AB itself. So AB upon AB will be 1. Now when the point C coincides with point B, angle C becomes 90. So we get cos 90 equals. Let us see what happens to BC. When points C and B coincide, length BC will become 0. So BC will be 0 and AC has turned into AB. So that will be 0. So we get two trigonometric values, sin 90 equals 1 and cos 90 equals 0. So we get these additional two trigonometric values. Now we will rewrite these values as sin 0 equals cos 90 equals 0, sin 90 equals cos 0 equals 1. So this is the collective representation of trigonometric values of sine and cos of 0 and 90 degrees. Now in order to find the trigonometric values of angles 0 degrees and 90 degrees, we will use the relationship which we have just found out, which is sin 0 equals cos 90 equals 0 and sin 90 equals cos 0 equals 1. Now we have tan equals sin upon cos and cot equals cos upon sin. So tan 0 will be sin 0 upon cos 0, that will be 0 upon 1, which will be 0. So tan 0 is 0. Cosec 0 will be 1 upon sin 0, which will be 1 upon 0. So cosec 0 will be undefined. Sec 0 will be 1 upon cos 0, which will be 1 upon 1, that will be 1. Cot 0 will be 1 upon tan 0, which will be 1 upon 0, and it will be undefined. Cosec 90 will be 1 upon sin 90, which will be 1 upon 1, that will be 1. Sec 90 will be 1 upon cos 90, which will be 1 upon 0, that will be undefined. Tan 90 will be sin 90 upon cos 90, which will be 1 upon 0, so therefore it will be undefined. And finally cot 90 will be cos 90 upon sin 90, that will be 0 upon 1, that will be 0. So this is how we can find trigonometric values of angles 0 degrees and 90 degrees. Let me put everything in a concise manner in a nutshell. First, science of trigonometric functions. For that, in order to decide the signs of trigonometric functions in different quadrants, we have to draw the two axes, x-axis, y-axis, and origin. This is first quadrant, this is second quadrant, third quadrant, and this is fourth quadrant. what we have learned is all trigonometric functions are positive in the first quadrant. Only sine and cosec trigonometric functions are positive in the second quadrant, and the remaining ratios are negative. Only tan and cot trigonometric functions are positive in the third quadrant, and the remaining ratios are negative. Only cos and sec trigonometric ratios are positive in the fourth quadrant, and the remaining trigonometric ratios are negative. This is how you can decide the signs of trigonometric functions. Next, we will see how to remember trigonometric values of some standard angles in a concise manner. All we have to do is to draw two right triangles. The first is a 30, 60, 90 right triangle and assign value 2 to its hypotenuse. Then assign a value of 1 to the side opposite to 30 degrees and assign a value of root 3 to the side opposite to angle 60 degrees. From this triangle alone, you will get 6 trigonometric values of angle 30 degrees and 6 trigonometric values of angle 60 degrees, provided you know the basic definitions of trigonometric ratios. Next, we will draw another right triangle, which is a 45, 45, 90 right triangle. We will assign a value of root 2 to its hypotenuse and the side opposite to 45 degrees, a value 1 each. Now, this triangle alone can give you 6 trigonometric values of angle 45 degrees. And finally, you have to remember a set of these relationships. Sine 0 equals cos 90 equals 0 and sine 90 equals cos 0 equals 1. This set of relationships, along with the trigonometric relations tan equals sine by cos and cot equals cos by sine, can give you another 6 trigonometric values for angle 0 degrees and 6 trigonometric values of angle 90 degrees. So therefore you can see here this triangle, this triangle, and these relationships, along with these two relationships, can help you create whenever you want 6 plus 6 12 plus 6 18 plus 6 24 plus 6 30. So in all, you can recall or you can create 30 trigonometric values from these set of relationships and these two triangles. Trigonometric identities. In the beginning of this video, under the topic of trigonometric functions, we have seen one trigonometric identity, which was sine square theta plus cos square theta equals 1. Now from this trigonometric identity, we will deduce two more trigonometric identities which are very useful in solving different problems. First, we will divide this identity by cos square theta. So that gives us sin square theta by cos square theta plus cos square theta by cos square theta equals 1 upon cos square theta. Now sin square theta upon cos square theta is tan square theta plus 1 equals 1 upon cos square theta is sec square theta. So we get our second identity, sec square theta equals 1 plus tan square theta. Its equivalent form will be sec square theta minus tan square theta equals 1. So these two equivalent forms are our second identity. For third identity, we will divide this first identity by sine square theta. So that gives us sine square theta upon sine square theta plus cos square theta upon sine square theta equals 1 upon sine square theta. This will be 1 plus cos square theta upon sine square theta will be cot square theta equals 1 upon sine square theta is cosec square theta. So the third identity that we get is cosec square theta equals 1 plus cot square theta, and its equivalent form will be cosec square theta minus cot square theta equals 1. So these two equivalent forms give us the third trigonometric identity. So these trigonometric identities are quite useful while solving problems on trigonometry. Friends, if you like this video, please click the like button. Share this video with your friends and classmates. Do subscribe this channel to get more videos of this type. See you in the next video. Until then, keep watching Number Collage. Thank you.